In this video, we are going to look at how merge sort is implemented in C++. If you remember, when I explained the algorithm, I told you that there is a subroutine called merge that takes two arrays of uh, uh, roughly size n over 2, and each array is already sorted because it's the result of a recursive call to merge sort, and then the merge subroutine merges those two sorted subarrays into one sorted array. And the majority, the the code that we're going to write today, most of it is going to be in a separate function called merge. Merge sort itself is going to be just dividing the array into two halves and then making recursive calls and then making a call to the merge function. So let's start with the merge sort itself. I'm going to use a template here to make it a little bit more general so that the same merge sort function can be applied to to arrays of different types. So it's going to be a void function. I'm going to call it merge sort. And for the parameters, it's going to have an array of type t, whatever t is. T later on when we call merge sort will be replaced by an actual type like int or char and so on. Then we need two indices. I'm going to call them begin and end. And the idea is that instead of actually dividing the array into two arrays, I'm going to work on the same array and two different regions of the array. Okay, so begin and end tell me from which index to which index the merge sort is being applied. So when we make a recursive call on the first half, instead of creating a new array with the size half of the original array, we just change those two indices to represent the fact that we are working on the first half. Or when I'm making a recursive call on the second half, again, I do the same thing. Okay, so that's the idea of begin and end. Now, to divide, now I need to find out where the middle index is. So mid is equal to begin plus end divided by 2. And then I need to make my two recursive calls, right? So I call merge sort on the same array A. And then for the left half, it starts at begin and ends at the midpoint. And the other recursive call is going to be to merge sort, same array. You see, I'm not creating two half arrays. I'm working with the same array, but by changing these two indices, in the first recursive call, I'm only working on the first half, and then on the second recursive call, I start from mid plus 1 and go all the way to end. So these are my two recursive calls. If you remember, divide and conquer, right? Divide here is not literally dividing into two, but just considering the first half and the second half separately by changing the two indices. And finally, when I'm done making recursive calls, I call the merge function that I will define after this. And the merge function is going to be taking the array itself, and then it needs to know where the two subarrays start and end. So the first one starts at begin and ends at mid, and then the second one starts at mid plus 1 and ends at end. So the merge function needs those three indices. It needs to know where the beginning, end, and midpoint is. And then it assumes that the array A is already sorted from begin to mid and from mid plus 1 to end. And it merges those two segments that are each one of them is separately sorted, merges them into one sorted region from begin to end. Okay, so that's the idea. Now, one thing that is missing here, and I want you to pause this video here and think about it. There is something missing in this definition. I mean, obviously I need to define merge, but other than that. So let's see if we can find that out. Now, probably you figured this out. This is a recursive function, but doesn't have a base case, right? So remember that when we talked about the base case, we said if we reach to an array that has a size less than 2, namely 1, then the merge sort function doesn't need to do anything, right? So we can put an if statement here that says if If begin is less than n, then do all of this. Then do all of this. Okay? Because, and just with 1D, because if you think about it, if begin is equal to n, then it means that we are starting, let's say, at index 5 and ending at index 5. So we are looking only at one element. So we are looking at an array or a segment of the array that has only one element in it. So in that case, merge sort doesn't need to do anything. The only case that the merge sort needs to divide and make recursive calls and all of that is if we have at least two. In other words, the base case here is kind of implicit. The base case is down here, something like this. Else, if the size is 1, then don't do anything, right? An empty else, but obviously we are not going to include that because it's just confusing, right? So here we go. Now we have our merge sort function. The only thing left to do is implementing merge. And this is going to be a little bit more involved. It's not that complicated, but a little bit more work. So again, I'm using template for this one. Type name T, void merge. It needs the array, obviously, and then it needs the three indices, right? Begin, mid, and end. Okay, so what I need to do is I need to create another array so that when I'm merging them, I copy that into the new array and then copy it back into the original one. So first I need to know what the size of that array is. So let's call that n, and that will be n minus begin plus 1 because it's inclusive on both ends. Right? When I say from index 2 to index 3, I mean including index 2 and index 3. So the size will be 3 minus 2 plus 1, right? So n minus begin plus 1. Now I need to create an array of this size using dynamic memory allocation. So T star, I'm going to call this result, is equal to the new operator. The type is T and the size is n. So create a new array of type T and of size n, and result is a pointer to the first element of that array. In other words, we can treat result as if it's the name of the array that we just created. And then if you remember from the previous video, when I explained the algorithm, there were three indices. One of them iterates through the first half, the other one iterates through the second half, and so on. And then the last one iterates through the result. So int left index. And the left part starts from index begin. So I initialize that to begin. And then I have the right index. And the right half starts from mid plus 1. Mid plus 1. And then finally, we had a result index that works with this new array that we just created. And that starts from 0. Okay, now we are ready for the actual body of the work, which is the while loop, if you remember. Let me fill in the condition later on for the while loop. But if you remember, we have these two subarrays. Each one of them is separately sorted. Now we want to put all the values in these two arrays into the result array, right? That's the idea. So if you remember, we compare the first element in the left half and the second and the right half. And whichever is smaller, we put it in the result, right? So if A at left index is less than A at right index, remember that our left and right halves are both A, right? We are not really creating two subarrays. We are working with A and using different indices, right? So if A at left index is less than A at right index, so the first element in the left half is less than the first element in the right half, then this is the element that needs to go into the result. So we say result array at result index should be the smaller value between the two, which is A at left index. Okay, now that we are done with that element in the left half, I need to move my index forward, so left index plus plus. And since I filled in one index in the result, I should say result index plus plus as well. So that's one case. The other case is if it is the other way around. If the right index is greater than the left index, or they're equal, right? In that case, I have to do the opposite, right? So in the else part, I say result at result index should be A at right index, because that is smaller or equal. And then right index should go up, and result index should also go up. Okay, so that's that. But how many times do we need to do this? If you remember again from the previous lecture, we do this until we reach the end of one of the two halves. If one of these two indices reaches the end and goes one step even further, then we shouldn't do any of this, because then we are looking at somewhere outside the range of the left or right. So the condition would be while left and right indices are both in the range. So I should say while left index is in its appropriate range, which is less than or equal to mid, right? Because that's the limits of the left half. And the right index is also in its appropriate range, which means less than or equal to end. Right? So this is the condition of the while. Now, the final thing to do, again, if you remember from the previous video, is that, okay, this is cool now, but when we get out of this while loop, when one of these two indices reaches the end. So we process one of the halves, either left or right, but one of them is not still done, right? There is one or more elements left in either the left half or the right half. So what should we do then is just copy whatever is left into the result, right? So I do that with a loop that says while left index is still less than or equal to mid, then copy everything. So exactly this. There we go. And also another one for the other half. So while right index still has room, so it has not reached the end, then do this. So copy everything that is left in the right half into the results. Okay, now note that because we are outside the first while loop, one of these conditions is going to be true. The other one is definitely going to be false, because it cannot be that neither one of them has reached its limit, right? So it's either that left index has reached mid and beyond, so then this while loop doesn't do anything and we only copy from the right half into the result, or vice versa. It could be that right index has reached its end, so we only copy from the left half into the results. But one of them is going to copy one or more elements into the result. And now result, remember the array result here, contains all the elements from the index begin to end in a sorted order. So what we need to do is now we need to copy everything back from the result to the original array, which was A. And that can be done with a simple for loop. For int I equals 0, I is less than n, I plus plus. And what I do is I say A at, remember in A, you start from index begin. So I say begin plus I is equal to result at index I. Now, everything in A from index begin to index end is sorted. And we don't need result anymore. And since we allocated the memory using the new operator, so dynamic memory allocation, it's our responsibility to deallocate it. And we do that by calling the delete operator. So I say delete result, and then result is equal to null, so that we don't have a memory leak here. And that's basically it. So this is your merge sort. And you see that most of the work is done in a merge, but it's not complicated. It's just considering different cases. Now, what's left to do in terms of studying merge sort is to talk about its running time. So let me go to the whiteboard and briefly talk about the runtime of merge sort. Okay, now what can we say about the runtime of merge sort? Unfortunately, the math behind it is a little bit more in depth than what I would like to talk about in a data structure series. If this was a series focusing only on algorithms, um, then I would give a full mathematical proof of the running time of merge sort. But as I said at the beginning, merge sort is significantly more efficient than the other two sorting algorithms. And more specifically, we can say that for merge sort, the runtime is order n log n in the worst case. Okay. Now, if you compare this with the previous ones, what we had for bubble sort and insertion sort for the worst case, for bubble sort and insertion sort, the worst case running time was order n squared. Order n squared time. Both of these are for worst case, right? Now you want to compare these two, n log n and n squared. So n log n, that's obvious, n times log n, and then n squared is n times n, right? So they have this n in common. So if you're comparing the order of growth of these two functions, basically what's left to compare is log n on this side and n on this side. And you should know from calculus or even before that, that n in comparison to log n grows much, much faster. So like imagine if this is log base 2, then if your n is 1,000, then log n is about 10. And if n is 1,000,000, then log n is about 20. So you see that as n grows, log n doesn't grow as fast at all, right? And that shows that n log n is much, much smaller than n squared, especially when n becomes larger and larger, when the size of your array becomes larger and larger. And as a result, merge sort is much faster than the other two algorithms, bubble sort and insertion sort. As I said, if you want to show, because for bubble sort and insertion sort, we analyze the nested loops to find out the time complexity. But for merge sort, because it's a recursive function, you need something called recurrence relations, and you need to be able to solve those, which is beyond the scope of the data structure course. But in my algorithm series, I will talk about that in more detail.